I am Dr. D.K. Tripathi, Assistant Professor of Physics under the Department of Basic Science and Humanities. In the last class, we have discussed in brief the initials of crystallography. Today, we will go ahead, and for that we will require some basic concepts. So let us discuss one by one all of them. The first one is coordination number. For a particular lattice, coordination number is defined as the number of equivalent nearest neighbors to a particular atom in the crystal lattice. That means coordination number is the number of equivalent nearest neighbors. Next is nearest neighbor distance. So it is defined as the distance between the centers of two nearest neighboring atoms in the crystal. You just keep in mind that the neighbors would be the nearest one. That means we will take the distance between the two very closely spaced neighbors. Atomic radius. Atomic radius is defined as half of the distance between nearest neighbor atoms in the crystal. Let us calculate atomic radius. So we will calculate the atomic radius of all three cubic structures one by one. So we will start with the simple cubic structure. Now before that we will have to take that atoms are spherical in shape and size. So for simple cubic structure, you see the radius r is equal to a by 2. Why? Because as shown in the figure, the total distance between the two atoms is 2r. From nucleus of one atom to the other atom is 2r. So because of that, we will have r equal to a by 2. The nearest neighbor distance d, that is 2. Now if we put the value of r as a by 2, we will get a. So the nearest neighbor distance d for simple cubic structure will be a. The atomic radius in case of body centered cubic structure will be as shown in the diagram. We are having AB is equal to root 2a, because AB is equal to root 2a. Due to that, AC square will be equal to AB square plus BC square. Now we have got the value of AB as root 2a, so we will put it there. Because of that, we will get AC square is equal to root 2a square plus a square. Now from that we will be able to get AC is equal to root 3a. Now what is AC? AC is equal to r plus 2r plus r as shown in the figure. So because of that, it will be equal to 4r. 4r is equal to root 3a. So due to that, r will be equal to root 3a by 4. That means we have got that the radius, atomic radius in the case of BCC structure will be root 3 by 4 into side, that is a. Now atomic radius in case of face centered cubic structure can be calculated using the figure shown. In the figure what we are getting that AB equal to A and BC equal to A. So from that AC can be written as root 2A, because AC is equal to AB square plus BC square. So due to that we will get AC equal to root 2A. Now it is visible in the figure that AC is equal to R plus 2R plus R again. So this will be equal to 4R. Due to that 4R is equal to root 2A. From that we will get R equal to root 2A by 4. So if root 2a by 4, root 2 will cancel 4 by 2 root 2. Due to that we will get r is equal to a by 2 root 2. So this will be the atomic radius in the case of face centered cubic structure, or we can write that atomic radius in case of face centered cubic structure will be 1 by 2 root 2 of side. Now we will discuss very important concept, atomic packing factor. This atomic packing factor is sometimes referred as atomic packing fraction, and this atomic packing factor of a unit cell is defined as the ratio of volume occupied by the atom in the unit cell to the total volume of the unit cell. So if we consider n atoms each of volume small v and capital V is the volume of the unit cell, then packing factor PF will be equal to N into small v by capital V. Now, sometimes this packing factor is expressed in terms of percentage. Atomic packing fraction of all three structures will be calculated one by one. So let us start with the simple cubic structure. In the case of simple cubic structure, we have seen that there is only one atom in the unit cell. So the volume of the atom of radius r is equal to 4 by 3 pi r cube, because we have considered the atom as spherical. So volume of the sphere 4 by 3 pi r cube. Here r we have got in the last, we have just got r as a by 2. So we will put the value of r as a by 2. We will get the volume of the atom as pi a cube by 6. Now the volume of the unit cell, the product of all three sides. So we have taken that unit cell is having the side dimension of a. So due to that, the volume of the unit cell will be equal to a cube. Now packing fraction. Packing fraction will be number of atoms into volume of atom by volume of the unit cell. So we'll put all these values. Number of atom is 1, volume of the atom is pi a cube by 6, and the volume of the unit cell is a cube. So a cube and a cube will cancel to each other, and because of that we will get pi by 6. Now if we put the value of pi by 6 as 3.14, then we will get this will be equal to 0.523. Now in terms of percentage, the packing factor of the simple cubic structure is 52.3%. That means the simple cubic structure is loosely bound structure because packing factor of it is less. Packing factor of BCC structure, body centered cubic structure. Now in the body centered cubic structure, we have seen that the number of atoms per unit cell is 2. So the volume of 2 atoms will be 2 into 4 by 3 pi r cube. Now 2 into 4 by 3 pi, and the value of r we have calculated earlier today in this class. So because of that, if we put the value of r as root 3a by 4, then we will get root 3 pi by 8 into a cube. Now packing fraction or packing factor will be equal to n into small v by capital V. Now what we know that small v is the volume of the atom and capital V is the volume of the unit cell. So the volume of the two atoms we have calculated root 3 pi by 8 into a cube, and the volume of the unit cell will be cube of all three sides, because each side is taken as with the dimension a. So the volume of the unit cell will be a into a cube. Now packing fraction will be equal to root 3 pi 8 cube by into a cube. So a cube and a cube will cancel to each other, and we will remain with root 3 pi by 8. Now if we put the value of pi as 3.14, then we will get 0.68, or we can say that the packing factor of BCC structure is 68%. So what we conclude? We conclude that the BCC structure is somewhat more hard bounded than the simple cubic structure. Although it is a loosely bound structure, but it is having more strength than the simple cubic structure. Packing factor of face centered cubic structure, FCC structure. Now we have discussed earlier that the number of atoms per unit cell in the FCC structure is 4. So therefore the volume of the 4 atoms will be 4 into volume of 1 atom. If we consider the volume of 1 atom as small v, so this will be 4v. Now 4 into 4 by 3 pi r cube. We have calculated the value of r as root 2a by 4. So we will put that, and because of that we will get the volume of 4 atoms as root 2 pi by 6 into a cube. Now packing fraction will be n into small v by capital V, where n is the number of atoms, small v is the volume of the atoms, and capital V is the volume of the unit cell. The volume of the unit cell will be a cube. So because of that, packing fraction will be equal to root 2 pi into a cube by 6 into a cube. Now a cube and a cube will cancel to each other. So we will remain with 0.74. In terms of percentage, the packing factor will be equal to 74%. So we conclude that out of 3 cubic structures, FCC structure, face-centered cubic structure, is having more strength because it is more, you can say that it is more hardly bound rather than the simple cubic and the BCC structure. So packing factor of FCC structure is 74%. So we conclude that it is hardly bound than the simple cubic and BCC structure. Lattice constants. The numbers A, B and C specifying the size of the unit cell, what we have called conventionally as unit cell, are called its lattice constants. For cubic lattices, we used to take a single number A which will serve as the lattice constant. So if A is the lattice constant, then the volume of the unit cell will be A cube, and if the volume of the unit cell is A cube and we take rho be the density of the crystal, then mass in each unit cell of the crystal will be rho A cube. Now if this will be the mass of each unit cell, then the mass of the molecule will be what? Again, if we take small n, number of molecules per unit cell, and capital M, the molecular weight, if capital N specifies the Avogadro number, then mass of single molecule will be mass of molecular weight by Avogadro number, that is M by N. Mass of each unit cell, that will be number of molecules in one unit cell into mass of single molecule. So number of molecules in each unit cell we have taken as small n, and mass of single molecule we have calculated capital M by capital N. So mass of each unit cell will be n into M by N. Now we have seen that we have taken that rho is the density and A cube is the volume of the unit cell. Then what we can write that the mass of each unit cell, that is mass of each unit cell, will be equal. That means equation number 1 and 2, both of them are giving mass of each unit cell of the crystal. So these two will be equated, and when we will equate equation 1 to equation 2, then we will get rho A cube is equal to n into capital M by N. From that we can calculate the lattice constant A. The lattice constant A will be equal to n into capital M by rho into capital N to the power 1 by 3, where A is called as the lattice constant, and this lattice constant determination is very vital in the case of the solid state physics, because with the help of that we will be able to measure the all three values of A, B, C. Let us discuss the importance of lattice constant in detail. So for that we have taken two illustrations here, and on the basis of these two numerical problems we will show that how much the lattice constant is important to the field of crystallography or to the field of solid state physics. As we know that numericals always confirms the theory, that is why we have taken the numerical problems for confirmation of the importance of lattice constant. So the first problem is, a cubic crystal has lattice constant 4.3 angstrom and density 963 kilogram per meter cube. If its atomic weight is 23, then what type of cubic unit cell does it form? That means we will have to tell the type of unit cell which will be formed using these data. Now we know that there are three types of unit cells: simple cubic, body centered cubic and face centered cubic. So we will have to tell that which type of unit cell will be formed. Now the lattice constant is given 4.3 angstrom. 1 angstrom equal to 10 power minus 10 meter. So because of that, A will be equal to 4.3 into 10 power minus 10 meter. Density is also given. This is equal to 963 kilogram per meter cube, and molecular weight is still given, that is 23. So because of that, when we will use the formula, N is equal to A cube rho N by M. We know the value of all of them. These values are given. The value of A is given 4.3 into 10 power minus 10. So we will put that. Then rho is also given 963. Avogadro number 6.02 into 10 power 23, and molecular weight is 23. So if we will put all these values, we will get the value of N will be equal to 2. That means number of atoms in the unit cell will be 2, and we know that number of atoms in the unit cell 2 is BCC structure. So because of that, we conclude that body centered cubic structure will be formed, because all these lattice constant rho and M are giving the value of small n, that is number of atoms, as 2. Now let us take the second illustration or second example, which is sodium chloride crystal has FCC structure and is of density 2.18 gram per centimeter cube. Calculate the distance between the two adjacent atoms. So here we will have to calculate the distance between two closely spaced atoms. Now we know that molecular weight of sodium chloride, the molecular weight of sodium chloride will be what? The molecular weight of sodium is 23 and the molecular weight of chlorine is 35.5. So when we will add them, we will get 58.5. So the molecular weight of sodium chloride will be 58.5. Now mass of a sodium chloride molecule, mass of a single molecule of sodium chloride will be molecular mass or molecular weight of sodium chloride by Avogadro number. So here molecular weight of sodium chloride is 58.5 gram mole divided by 6.023 into 10 power 23 per mole. So this will give us 9.713 into 10 to the power minus 23 gram. So mass of a sodium chloride molecule will be got as 9.713 into 10 to the power minus 23 gram. Now next is to calculate the number of molecules per unit volume. Number of molecules per unit volume will be equal to mass of unit volume of sodium chloride by mass of sodium chloride molecule. Mass of unit volume of sodium chloride is given 2.18 and mass of sodium chloride molecule of a single molecule we have calculated just 9.713 into 10 power minus 23 gram. So this will be equal to 2.18 by 9.713 into 10 to power minus 23. So we will get 2.244 into 10 power 22 molecule per centimeter cube. Now the number of atoms per unit volume of sodium chloride. So that will be equal to, as we know that sodium chloride is a diatomic molecule, so this number of molecules per unit volume will be multiplied by 2. So we will get number of atoms per unit volume of sodium chloride will be 2 into 2.2 244 into 10 power 22. If we take A and small n as distance between adjacent atom and number of atoms along the edge of 1 centimeter cube, then the length of the edge of the unit cube will be n into A. So volume of the unit cube will be n cube A cube. So here we have taken that volume of the unit cube is, unit cube volume means 1 into 1 into 1, that is centimeter cube. So 1 centimeter cube is equal to n cube by A cube. Now we have calculated the value of small n. This is what? This is 2 into 2.244 into 10 power 22. So we will put the value of that and we will get 2.2 into 2.244 into 10 power 22 cube into A cube equal to 1. So from that we will get the value of A as 1 by 2 into 4 into 10 power 22 to the power 1 by 3, which will give us 2.81 into 10 power minus 8 centimeter. Now 10 power minus 8 centimeter equal to 1 angstrom. So volume of the unit cube will be 2.81 angstrom. These are some of the references which you must pursue to know more about the topics. Thank you.